The persistent store manifest is a structured metadata file that indexes all serialized objects within a data store instance. It maintains a registry of object identifiers, their physical locations on disk, and their interdependency graph. The manifest is written incrementally as objects are committed, with periodic flush operations to ensure durability. The format is intentionally simple to minimize parsing overhead during recovery sequences. The manifest header occupies the first 256 bytes and contains version information, creation timestamp, and a checksum of the entire file structure. The version field is a 32-bit unsigned integer. The creation timestamp is stored as milliseconds since Unix epoch in a 64-bit unsigned integer. The checksum uses CRC32 polynomial and is recalculated after every write operation to the manifest. Following the header, the manifest contains a sorted array of object records. Each record is 128 bytes and includes the object identifier as a 16-byte UUID, the segment number as a 32-bit integer, the offset within that segment as a 64-bit integer, and the serialized size in bytes. Records are sorted lexicographically by object identifier to enable binary search during lookup operations. The dependency section of the manifest tracks relationships between objects. Each dependency entry is 32 bytes and contains a parent object UUID, a child object UUID, and a 16-bit relationship type identifier. This structure allows the system to traverse the object graph during garbage collection and dependency resolution without loading objects into memory unnecessarily. Object records may contain optional metadata fields appended after the core record. These fields are variable length and preceded by a 16-bit type identifier and 16-bit length. Common optional fields include content hash, compression indicator, and custom user tags. The manifest parser must skip unknown optional field types gracefully during reads. The manifest maintains a free space index that tracks unused regions within allocated segments. This index allows the allocator to reuse deleted object space efficiently. Each free space entry records the segment number, start offset, and size of the available region. The free space list is maintained in offset order within each segment to facilitate coalescing adjacent free regions. Segment metadata within the manifest includes the segment identifier, maximum size, current utilization, and last modification timestamp. Each segment entry is 64 bytes. Segments are assigned sequentially upon creation and are never reused. The manifest tracks which segments are active for writes and which are sealed for archival purposes. The manifest implements an index table after the main object records section. This index maps object identifier hash values to byte offsets within the manifest file. The hash function is a simple 64-bit variant of FNV1A. Index collisions are resolved through linear probing. The index table is always power of 2 size for efficient modulo arithmetic. When a manifest reaches a size threshold, typically 100 megabytes, a compaction operation is triggered. During compaction, a new manifest file is written that removes all deleted object entries and coalesces adjacent free regions. The compaction runs offline and does not block ongoing read or write operations. Upon completion, the old manifest is atomically replaced. The manifest file is accessed through a memory-mapped interface for performance. The first 256 bytes are always kept in main memory to avoid repeated disk access. The index table is typically cached in an in-memory hash table for fast lookups. Cache coherency is maintained through timestamp comparison with the on-disk manifest. Recovery from a crash begins by reading the manifest header and validating the checksum. If the checksum fails, the system attempts to read the previous manifest version from a secondary location. Each manifest write operation creates a backup copy with a timestamp suffix. The recovery process loads the most recent valid manifest found. Object deletion is recorded in the manifest through a soft delete mechanism. Instead of removing the entry, a deletion timestamp is added to the optional metadata fields. Soft deleted entries remain visible to the dependency resolver until the next compaction cycle, allowing for recovery within a configurable retention window. The manifest supports multiple concurrent readers through read-write locking. Write operations acquire an exclusive lock before modifying the manifest. Reads acquire a shared lock to ensure consistency. Lock acquisition timeout is set to 30 seconds with exponential backoff. Deadlocks are detected and reported through the logging subsystem. Periodic integrity checks validate the manifest consistency. These checks verify that all referenced segments exist, all dependency pointers are valid, and free space regions do not overlap. Integrity checking runs asynchronously and logs findings to a dedicated audit stream without blocking normal operations. Automatic repair is available as an optional configuration parameter. The manifest implements versioning for forward and backward compatibility. The version field in the header indicates which object record format is in use. Older reader implementations can recognize unsupported version numbers and gracefully degrade or report an error. New versions extend the record structure with additional optional fields rather than modifying existing fields. Export and import operations serialize the manifest to a portable format. The export format is aligned a limited JSON representation where each object record becomes a separate object string. This format is human-readable and suitable for backup and migration purposes. Import operations validate each record before insertion to ensure data integrity.